Hello, I'm Brian Humphreys, Director of Communications for Autonomous Systems and Advanced Programs at Northrop Grumman. Recent times have seen some amazing advances in autonomous systems, from self-driving cars on our highways to unmanned planes the size of 757s monitoring our oceans. These individual systems are changing our lives. Imagine then the advances when autonomous systems begin to collaborate with each other and with their commanders. Today I'm with Richard Sullivan, Vice President, Advanced Programs at Northrop Grumman. Thank you, Richard. We're going to discuss advances in autonomy and in particular how systems and people will work together. Where do you think the next advances in autonomy will be coming from?
Great question. When you think about where we are today with autonomous vehicles on the road, with the automatic cruise control for one, and when you look at where the airplanes have gotten with their autopilots, those are really, I'll say, the first step of autonomy. And as we look at where we're going forward with how much you can, I'll say, rely more on the computer systems within the vehicles to take the systematic steps that are, I'll say, the routine steps and have the computers and the autonomy take those things over, you can see that blossoming through all levels of technology all across the environment, whether it's in airplanes, whether it's in spacecraft, whether it's in ground vehicles, whether it's in undersea vehicles. It's going to be exploding through all of those domains.
You mentioned advanced autonomous aircraft. Northrop Grumman was responsible for, or is responsible for, one of the, arguably, the most advanced unmanned aerial system in the world today, the X-47B. Can you tell me what's so special about the X-47B?
You know, we love to talk about the X-47B. It won the Collier Trophy in 2013. It was on sea trials from 2012 to 2015. World's first autonomous aircraft to do carrier takeoffs and landings. In 2015, the world's first fully autonomous aerial refueling. When you look at the technology that was developed in the early 2010s and how much we've continued to invest and advance that autonomy, what we see going forward is just going to blow everybody's mind away.
What are some of the challenges when it comes to getting an unmanned aircraft to land on an aircraft carrier?
Well, first of all, it's about trusting the software and trusting the algorithms. One of the things that we have with our modern digital engineering and the Agile Enterprise is use modeling and simulation to test hundreds to thousands to hundreds of thousands of trials, adjusting each of the parameters that the aircraft may see, and understand under all the conditions through an actual operation, we understand and trust what the vehicle is going to do.
The X-47B had to operate on an aircraft carrier alongside manned aircraft. What were some of the challenges that you had to address in having that unmanned system operate on a day-to-day basis with manned aircraft?
You know, a big part of it was the fact that there wasn't a human in the loop, right? A human in the loop. What we had was a human on the loop. When you look at the operations on the aircraft carriers, what we had to make sure is that we had responsive control of the X-47B. In other words, there's a human on the loop, not a human in the loop. In other words, the pilot's sitting within the computer itself, but the operator, the commander, knew what the airplane was going to be doing. So there was tight operations for takeoffs alongside an F-18, landing where they had to pull the X-47B off before an F-18 landed. That all was tightly orchestrated with both the Northrop Grumman employees as well as the great collaboration with the U.S. Navy.
The X-47B also proved the ability to refuel air-to-air behind a manned tanker. Can you tell me what's so significant about that achievement?
Very specifically to the tanker, it's really one of the first things when we talk about manned-unmanned teaming, which I think is really, really interesting on a lot of things that we're talking about today. The ability for the X-47B to approach and connect with the tanker showed how the trusted autonomy was validated and implemented in a real-world scenario.
You talked about manned-unmanned teaming. While you were working on the X-47B, you were also looking at another type of teaming of unmanned systems with a program called DARK. Can you, A, explain what the acronym stands for and why it's so special?
Right. So DARK is our technology that we call distributed autonomy and responsive control. What distributed autonomy means is how we can implement autonomy within the vehicles themselves, as well as within the mission management station. Responsive control is about making sure that operators have the ability to understand what the vehicles are going to be doing with their autonomy and be able to take over if they need to.
So what are some of the benefits of distributed autonomy?
The benefits of distributed autonomy is that you're able to have fewer operators managing a larger number of resources. And the best part is you can have a heterogeneous type of vehicle. So you can have different types of vehicles with different types of sensors operating with a small crew, a small human operator set that's able to manage the objective. The mission objective is what they're looking to accomplish, not what is the next point on the blue line they're going to be flying to.
Perhaps you could give us a scenario where responsive control demonstrates its value, or a scenario that demonstrates the value of responsive control.
A good example of the value of responsive control is if you have a mission space that you're trying to accomplish, and you may set certain constraints within the system to say, if I get this low on gas, I'm going to have my aircraft, come back home so that they can hit the tanker or they can go all the way back to base. But in certain scenarios, you may want to extend the operational footprint. You may be willing to push into those margins. So the operator can take over that scenario and say, hey, I'm going to push into the margins a little bit here because what's going on in other aspects of the mission still need to have resources that are staring at them.
So what are some of the types of missions that DARC could be used for?
The types of missions that we would see DARC being used for is one, I'll say the more boring missions where, let's say you're looking across a vast ocean, looking across a vast desert, just watching any potential ingress or egress of an area that you're doing overwatch on that's 24/7, 365 with sensors that are just looking for anything to happen. That's one example, and the other side of the example would be where the missions could be extremely dangerous, and you can use multiple assets that are going to be adjusting and adapting to how the environment is changing.
So just to be clear, when you're talking about, let's look at that ocean scenario for a moment. So you're talking about how many unmanned systems operating in an environment. So how many systems can DARC control, and how would they share workload?
It's a scalable system, so there isn't really any limit. It's a limit of the computers and the processing that you'll have in your building, type of a thing. How they share the workload, it really then goes on to what the sensor footprints are. So if you're using wide area surveillance radars looking at the north coast of an island, you can be just watching the sea for any types of incoming ships that may be useful in different scenarios. And how you cover that is going to then drive how many vehicles you need to cover that. 24/7, is it certain things that get triggered, tripwires that get triggered that determine when you have to go or what you need to look for. So it's all user definable.
Maybe you can give us another example of a real-world example of how DARC would be utilized.
Something that keeps me up at night working in this industry now for a little over 25 years is how can we use this system to help scenarios, really bad scenarios like a downed pilot scenario. And we see the environment with the threat levels going up and how the threats are dynamic. That's really where something like DARC will really be beneficial, where we have multiple vehicles that are in the area of regard, some of them with different types of sensors. How can we find the pilot? Where was the last known information? And how can we use all that information to optimize the different vehicles to look for this downed pilot? And when we think about that is each of the vehicles may have already been on a mission. They have different levels of fuel. They can't go and engage. We have different scenarios where they're still keeping an eye on other parts of the battle space, so they can't get engaged. And when we ask a human operator in the loop to make all these decisions with everything going on simultaneously with his buddy somewhere down in the field, right? Let's let the operations that the computers can do best, which is solve really complex math problems really quickly. and let the human operator take advantage of the things that they do best, which is manage a scenario and find other ways to bring assets in to support it. Because as soon as something like a dark system finds it, we're going to have to go and send in helicopters, send in rescue, send in A-10s, whatever they need to have to protect and save our warfighters.
So in the dark scenario, if one of your unmanned systems, that perhaps the one that's taken the task to go and get that downed pilot, if it loses communications or it gets into a storm, what happens with dark?
So what happens with dark in a scenario where you have a comms challenge or a weather challenge is the scenario adjusts, right? So the objectives of the mission still exist, but the constraints of how you perform the mission have changed. And that's the greatest thing is when you have these dynamic scenarios or changing scenarios, dark will continuously adjust to those scenarios.
So another air vehicle will take over that task automatically?
Yes, that's correct. So the task allocation then gets assigned to another vehicle that is best suited to take over that mission.
Digital transformation is changing the environment for everyone, both the commercial environment, the civil environment, and the military environment. It's creating some significant challenges for the commanders. So can you talk a little bit about how dark helps address those challenges?
Right, so the digital transformation it happens on both sides. So the complexity of the threats that we're going after is making the commander's job significantly more complex as well. And what we see is how autonomy is going to help, I'll say, provide force multiplication to the commander in terms of understanding that certain decisions that the aircraft are making are being made because it's the best decision considering the inputs that it has. So it really becomes a force multiplier for whether it's a mission commander and a military application, it could be a commercial application, it could be a science application. How can we leverage autonomy to take advantage of the exponential amount of inputs that we're seeing from the environment, the sensors, the aircraft, the threats, all across the spectrum?
The challenge is, though, that in the digital space, threats are infinite and they're only becoming more numerous. So that's where dark comes into play.
Yeah, dark comes into play when you have more things than a human can accomplish in terms of trying to satisfy these tasks in this increasingly complex environment.